Right, kids, question 4. This was our solids under stress question, our Young's modulus, our stress over strain, etc., etc. But it had a high amount of marks dedicated towards uncertainties in this question as well. One of the questions in the paper will have some marks dedicated to uncertainties. And on this paper, it was this one. So standard question about working out Young's modulus, going to put a weight on a wire, measure the extension, and do the normal equation, stress over strain, where stress is force over area, strain is extension per unit length, right? So here's some of the readings they did. They've given us the resolution of the apparatus to take these readings. And we've got to work out some uncertainties using these readings here, okay? So we've practiced this in class. Calculate the cross-sectional area in meters squared and show that the percentage uncertainty is approximately 11%, right? And there's a reason these are in bold. Obviously, percentage is in bold, and they've told us what the answer is going to be. They don't want an absolute value, they want it as a percent. And they're reminding us that this area is pi r squared, it's in meters squared. And of course, when one of the measurements is squared, you've got to multiply by that index when you're working out the uncertainty. So here's my value for area, right? Pi times radius squared. Don't forget, it's got to be in meters. So if the diameter is 0.18 millimeters, I want my radius as 0.09 times 10 to the minus 3 meters, right? They've asked for it in meters squared. Chuck that in. That gives me 2.5 times 10 to the minus 8 square meters. That is the cross-sectional area of the wire. But we've got to work out the percentage uncertainty of that measurement. So it's the resolution of the piece of apparatus, they've told us, is 0.01 millimeters. Times by the index, the power that is being used. Now it's squared, r squared, so I've got to have a times by 2 there. Divided by the reading that was taken, 0.18 times 10 to the minus 3 meters, and then turn it into a percent. Chuck those numbers in a calculator. Comes out as 11.1 recurring percent. That's pretty much close to approximately 11%. Happy days. And then for 1 mark, show why the uncertainty in the length reading can be considered negligible. So same thing. It's the resolution of the instrument. And when we measured the length, the resolution was 1 millimeter. So that's 1 times 10 to the minus 3. Length doesn't have a power. Well, it does. It's to the power of 1. Okay, so I just need to times that by 1 or not bother writing it. Divided by the reading. The reading was 1.94 meters. Turn it into a percent. 0.05% uncertainty we can consider negligible. Happy days. Right. Then they ask us to determine the Young's modulus of the metal, right? So the only force acting on it is the force due to gravity, 9.81. The original length they told us was 1.94. We just worked out the cross-sectional area, 2.5 times 10 to the minus 8, and they told us the extension was 6 millimeters. Don't forget everything's in meters though, so that's 0.006. Chuck a line to the calculator. We are always expecting for a steel wire a power of times 10 to the 11, so I'm quite happy when my calculator says 1.27 times 10 to the 11 pascals. Right, back to uncertainties again now. Karen is told that the percentage certainty in the load is 5%. Use this information to calculate an absolute uncertainty. So to get this absolute uncertainty, we're going to add up all the uncertainties as percents and then work out that percentage value of our Young's modulus reading, and that'll be our plus and minus that goes on the end, okay? So they tell us that the uncertainty of force, they just told us, is 5%. The length we worked out was negligible. The uncertainty of area we worked out was 11%. Also, they told us that. So they've told us this one, and this one so far. It's the extension uncertainty percentage we've got to work out. So it's the usual thing. The resolution of the instrument plus or minus 0.5 millimeters. So that's plus or minus 0.5 times 10 to the minus 3 meters. Times by any index. If it's r squared or r cubed for volume, it's not. Extension is a length. That's just times by 1. Divide by the measurement. They told us the measurement, 0.006. Turn it into a percent is 8.3. So I'm going to add up these 3% to get my total uncertainty percentage. Work out 24.3% of my Young's modulus value, and that's my absolute uncertainty, okay? So it's 1.27 times 10 to the 11 pascals plus or minus 30.87 gigapascals. Right? I put a G there instead of the 10 to the 9. Right, happy days. Next one, only with 2 marks, so it can't be that tricky. We got 5 types of metals. We got 5 of the... I do apologise. It does say give your answer in gigapascal. That's why I did that there. Here's 5 metals. Here's a Young moduli in gigapascal. Karen's friend Jack determined the Young's modulus to be 126 plus or minus 20. They both use the above table to determine the metal in their wires. Discuss how Jack's conclusions differ from Karen's, right? So Jack, plus or minus 20, can go from 106 to 146. So that's just bronze and copper. Oh no, it's not even bronze, it's 103. So Jack has only got copper. Whereas Karen could go all the way down to 97-ish, up to 157-ish. So that allows bronze, zinc, and copper. So that's how they differ. No problem there. And then the last one for 3 marks. So they want 3 points. Suggest differences in the way Jack carried out his experiment. He had more time to do it. And they want some suggestions on how he analysed his results, which led to those difference in results, right? So I could think of 4 things. The obvious one is he took more readings and found a mean area. That's a much more accurate way of doing it. He could have used a heavier weight on the end, which would have produced a longer and more measurable extension. Another stock answer. He could have used better equipment with higher resolution, and that would reduce the amount of uncertainty. And this was the one they was looking for in the way he analysed his results. He could have drawn a force extension or a stress strain graph, and by finding the gradient of that would have determined the Young's modulus. Right, so all pretty standard stuff there in your notes. Get learning, get revising, get passing this exam. Goodbye.